Welcome to QOD 51, in which we now progress into Chapter 11. Chapter 11 is nominally about liquids, but it's also about relationships between the three fundamental states of matter, as well as, most importantly, and what the subject of this video is going to be, what we call intermolecular forces. But just to quickly remind ourselves, sort of what's the difference between a gas, a liquid, and a solid. A gas has a fairly low density, it's compressible, it will assume both the volume and shape of its container, and it's compressible, it'll expand or contract if we change the volume of the container. A liquid is going to assume the shape of the portion of the container it occupies, but it doesn't expand. It's pretty much incompressible. A solid is going to retain its own shape and is also incompressible. The densities of liquids and solids are pretty much the same for a given substance. And so because the particles are in contact with each other, and so we refer collectively to liquids and solids being what we would call the condensed phases. And so the state of a substance, whether it's going to be a liquid, a solid, or a gas at a particular temperature, is really dependent on two things that are kind of opposing each other. One is the kinetic energy of the particles, that is, how fast are they moving or how fast are they trying to move and trying to sort of bust apart from each other. The second would be the attractive forces that are holding those particles together. We refer to those attractive forces collectively as intermolecular forces, and that's the subject of this video. And so just to kind of bring this idea home, if you think about, so here's an example of a gas, chlorine gas, a liquid, bromine, and a solid, iodine. These three have been deliberately chosen because they're all the halogens. Remember, halogens form diatomic molecules. And if you drew Lewis structures of these and looked at them, they would look pretty much identical. Chlorine will have a total of a single bond with a total of 14 valence electrons. Bromine, a bromine-bromine single bond with a total of 14 valence electrons. Iodine, an iodine-iodine single bond, total of 14 valence electrons. They're all nonpolar. So why is it that chlorine is a gas at room temperature, bromine's a liquid at room temperature, and iodine is a solid at room temperature? Well, we're going to try and answer those questions in the subsequent slides. So intermolecular forces are the forces that cause the molecules of a particular substance to be attracted to each other. We're not talking about the covalent bonds within a molecule. We're talking about weaker, yet nevertheless significant attractions that cause multiple molecules of a particular substance to be attracted to each other. Why does water condense into a droplet rather than just stay as a gas? Intermolecular forces, regardless of the type that we're talking about, are Coulombic attractions, that is, electrostatic attractions between partial charges in a molecule. And so you will have a partial positive charge in a particular part of a given molecule and a partial negative charge in another part of another molecule. And those things will be attracted to each other, and that's the basis for intermolecular forces. And we can really think of we've already encountered what would really be the most extreme case of intermolecular forces, in which you have a total separation of charge, and that would be ionic bonding. And we've already talked about the strength of ionic bonding and its effect on physical properties when we were talking about lattice energy. Okay, so let's talk about what we're talking about. Intermolecular forces are not the covalent bonds that are holding atoms together in a molecule. What they are weaker attractions that hold two or more molecules of a given substance in contact with each other. So this is a covalent bond, the straight line. This dot, dot, dot represents the intermolecular attraction between two hydrogen chloride molecules. They're not as strong as covalent bonds, but they are strong enough to affect the physical properties of the various substances. And so the strength of the intermolecular forces is going to determine what temperature a thing melts at, what temperature a thing boils at, as well as other properties like viscosity and vapor pressure and stuff like that. And we can refer to the three types of intermolecular forces that we're going to focus on now as collectively as van der Waals forces. So what are those three intermolecular forces that we're talking about? The first we're going to talk about is what is called dipole-dipole interactions, which is a pretty straightforward thing to try and understand. Then we'll talk about what are called London dispersion forces. Finally, we'll talk about hydrogen bonding. And if you've had a biology class, for example, in which we talk about hydrogen bonding as the way that water molecules stick to each other, or that the nitrogenous bases in a DNA double helix stick to each other, you're familiar with the concept of hydrogen bonding. Okay, let's start with dipole-dipole interactions, which to my mind is the sort of most straightforward thing to understand. In order for a molecule, for a substance, to exhibit dipole-dipole interactions, that molecule has to have a permanent dipole. It has to be a polar molecule. And so the example that we're talking about here is a molecule called acetonitrile. There's a CH3, then a C, then an N. And that is polar because hydrogen is less electronegative than carbon. Hydrogen in the white is less electronegative than carbon in the black, and carbon is less electronegative than nitrogen in the blue. So if we drew a dipole arrow, you would indicate that this blue end of the molecule is partially negatively charged, and the hydrogen end of the molecule is partially positively charged. And if you look at this crystal structure of acetonitrile in the solid phase, you will see that these molecules are all aligned, so that the hydrogen or positive end of each molecule is aligned with the nitrogen or negative end of each neighboring molecule. And they're locked into this lattice in which it's all head to tail, head to tail, head to tail. In the liquid phase, these things are tumbling around, so they can't really lock themselves into a head to tail like you can in the solid phase, but you'll still see that the red intermolecular forces, which is head to tail, are much more predominant than the blue ones, which would be repulsive, which would be tail to tail or head to head. And so that's what causes acetonitrile that's what determines things like its melting point and its boiling point, is how strong these attractions are between the negative end of one molecule and the positive end of a neighboring molecule. That's dipole-dipole interaction. And they grow increasingly strong with the polarity of the molecule. And so what we have in this image actually is 4 different molecules: propane, dimethyl ether, acetaldehyde, acetonitrile, all of which have nearly very similar formulas, very similar in shape and size. You'll notice that they're very similar in molar mass, ranging from 41 grams per mole to 46 grams per mole. The big difference in them is what's known as their dipole moment, which is a measure of the strength of their permanent dipole. And you can see that the dipole moment goes from essentially 0 in propane, which is not a polar molecule, up to 3.9 dBi in acetonitrile, which is a very polar molecule. And you can see that as the dipole moment goes up from 0.1 to 1.3 to 2.7 to 3.9, that the boiling points of all these things go up. And that is a trend that you will see in polar molecules of similar size. So that's dipole-dipole interactions, the electrostatic attraction between the positive end of one polar molecule and the negative end of another polar molecule. And the requirement there is that you have to be polar in order to exhibit dipole-dipole interaction. The next type of intermolecular force we want to talk about are what are called London dispersion forces. And this is a little bit more subtle, but not that difficult to understand. And what we're using as our example here is a couple of helium atoms. Now, helium atoms have 2 electrons, and because electrons tend to repel each other, it's generally the case that the electrons in a helium atom are going to, at any particular time, are probably going to be as far away from each other in that atom as they can be. And as a result, there is no dipole, there is no permanent dipole in a helium atom. And that's what this image is trying to show, that there is, in general, an equal distribution of charge throughout the entire atom. There's no permanent dipole. But it's also the case that electrons are just flopping around all the time, and while they tend to be as far away from each other as they can get, occasionally they won't be. And so it can just happen as a matter of chance that at any particular moment in time, both electrons might be on the same side of the helium atom. What that does is to, just for a moment, give that helium atom a transient or temporary, what we would call instantaneous dipole. Because at this particular moment in time, both electrons happen to be on the left-hand side of this helium atom, it will acquire a slight partial negative charge on this side and a slight partial positive charge on that side. And so this model here is reflecting the fact that in this atom, the electrons are equally distributed, whereas in this atom, they just happen to be both on the same side. So this atom has no instantaneous dipole at the moment. This atom does. Well, there's a curious effect to this, and that is if an atom acquires an instantaneous dipole, it's now going to affect the atom next to it and induce an instantaneous dipole in that atom. So originally we had no dipoles at all. Now atom B obtains a transient instantaneous dipole. It now induces a dipole in atom A. And this just kind of keeps going along the line. Like you might see a little breeze going over a wheat field in which one wheat stalk bends over and then pushes over the next wheat stalk and pushes over the next wheat stalk. And as that goes down the line, then maybe the original one sort of snaps back up again. So if you had a collection of helium atoms, you would get this induced dipole, say, in one atom here, and that would sort of spread to the ones around it, and it would sort of spread out like ripples on a lake and then eventually kind of snap back. But it's those induced dipoles that attract each other slightly, and that is what we call London dispersion forces. And so a dispersion force is the electrostatic attraction, the Coulombic attraction between partial positive and partial negative sides of molecules that do not have permanent dipoles, but that have had a temporarily induced dipole. Now, all substances exhibit dispersion forces, whether they're polar or nonpolar. But dispersion forces are the only intermolecular forces that are exhibited by nonpolar atoms or by nonpolar molecules. And the size of that electron cloud, and it's kind of ironic that they pick helium as their example, because helium has basically the smallest electron cloud of any atom on the periodic table. But the size of that electron cloud is referred to as that atom's polarizability. And actually, the larger that electron cloud is, the more polarizable we would say that atom is. Well, there are factors that affect the strength of London dispersion forces, and one of them is shape. And so these are two isomers of pentane. They both have the same formula, but their shapes are different because their carbon connectivities are different. We've talked briefly about isomers before. This has more of a linear shape, N-pentane. What's called neopentane has more of a spherical shape. Because the N-pentane molecules can kind of stack better because they have this linear shape, they can have more surface area contact with each other. There are stronger dispersion forces between pentane molecules than there are between neopentane molecules. And you can see that that's reflected in difference in boiling point. These pack together better, they've got stronger intermolecular dispersion forces, therefore a higher boiling point than neopentane, which doesn't pack as well, less surface contact between molecules, weaker intermolecular forces. The other thing has to do with the size and polarizability of the molecule or the atoms themselves. And this really goes back and answers our question that I posed at the very beginning of this presentation, which is, why is it that because Cl2, Br2, and I2, despite the fact that if we think of them as Lewis structures in polarity, they're essentially all identical, why is it that chlorine is a gas, bromine is a liquid, and iodine is a solid at room temperature? That has to do with polarizability. An iodine molecule is much larger than a bromine molecule, which is much larger than a chlorine molecule, and therefore the polarizability is greater, the strength of the dispersion forces is greater, and that affects the melting point and the boiling point, making one a gas at room temperature, one a liquid, and one a solid. This is also true as you look at the noble gases, that the larger they get, the more polarizable they get, the stronger their dispersion forces, and the greater their boiling points. These are all nonpolar atoms or nonpolar molecules, but the larger that they are, the stronger the dispersion force. Now, what about comparing dipole-dipole interactions to dispersion forces? Which are stronger? Well, on an atom per atom basis, if we're talking about two molecules that have essentially very similar shapes, very similar sizes, and very similar molar masses, then dipole-dipole interactions are going to be a stronger intermolecular force because that's a permanent dipole, and so you've got a fairly strong attraction there. Whereas dispersion forces are the weak interactions between transient dipoles. But if you have one molecule that's quite a bit larger than another, then dispersion forces are actually going to predominate. And so an example I've just come up with here is to compare methanol. Methanol not only is a very polar molecule with a very large dipole moment, it also exhibits hydrogen bonding. Whereas octane is a completely nonpolar molecule, just made up of a chain of 8 carbon atoms in a row surrounded by hydrogen atoms. No dipole, and therefore this only exhibits dispersion forces. Nevertheless, it has a much higher boiling point than the methanol, and the reason is because octane is just so much larger. On an atom per atom basis, the dispersion forces are weaker than they are than hydrogen bonding or dipole interactions. But because this molecule has 8 heavy atoms and this one only has 2, then octane has a much higher boiling point than methanol, because in total its dispersion forces are stronger than the dipole and hydrogen bonding in methanol. Well, that gets us to the concept of hydrogen bonding, and so this is a very interesting graph. I don't feel like I really have a lot of time to unpack it here, and so if you want to take a look through this in your textbook, you may. But what it's really showing here, if you just take the chance to stop this and look at it if you want, is that when it comes to intermolecular forces, that ammonia, hydrogen fluoride, and water are just outliers, and they're doing strange things compared to the trends in intermolecular forces of these other substances here. And that's due to a phenomenon that we would call hydrogen bonding. And so let's just define what hydrogen bonding is. Hydrogen bonding is a special kind of dipole-dipole interaction that's almost kind of halfway between a dipole-dipole interaction and an ionic bond. And it's exhibited by compounds that contain a nitrogen-hydrogen bond and or an oxygen-hydrogen bond and or a fluorine-hydrogen bond. And we call these hydrogen bonds, and it really arises from the fact that let me just go forward a little bit. It arises from the fact that nitrogen, oxygen, and fluorine are very, very electronegative. So, whereas hydrogen has a fairly low electronegativity, and therefore an NH bond, an OH bond, or an FH bond is very, very polarized. There is a tremendous amount of negative electron density around a nitrogen, oxygen, or a fluorine in a bond like that. And on the hydrogen end, that it has lost almost all of its electron cloud, and there's a very large partial positive charge um, on the hydrogen atom in one such bond. And so what you can get is these nearly kind of halfway between a dipole-dipole interaction and a ionic bond occurring between the hydrogen atom of the very positively charged hydrogen atom of one molecule and the very negatively charged oxygen atom of an adjacent water molecule. And so you can get hydrogen bonding between water molecules. You can get hydrogen bonding between hydrogen fluoride molecules. You can get hydrogen bonding between ammonia molecules. The other thing you'll see, and this is really what happens, say, for example, in the hydrogen bonding that occurs in nucleic acids, is you can get hydrogen bonding between two different types of molecules. Because water has a highly polarized OH bond, but ammonia has a very partially negatively charged nitrogen atom, you can get a hydrogen bond between a water molecule and an ammonia molecule. Or on the reverse side, you can get a hydrogen bond between the hydrogen of an ammonia molecule and the oxygen of a water molecule. So you can get hydrogen bonding within a particular substance, like we're showing here, but you can also get hydrogen bonding between different substances, provided that they have an OH bond, an NH bond, or an FH bond. Okay. That I think is well, so I'm sorry, let me just go on and say just briefly one more intermolecular action we want to talk about. It's what's called an ion dipole interaction. And that simply means that if you have an ionic substance, it'll often tend to be, say, soluble in a very polar liquid, water being the great example. So here is what happens. So ion dipole interactions are exhibited, say, when you dissolve sodium chloride, that is table salt, in water. The chloride ions get hydrated by the water molecules, in which the partially positive ends of the water molecules align themselves with the negative chloride atom. The sodium atoms get solubilized because the partially negative sides of the water molecules align themselves with the positively charged sodium atom. So that is called an ion dipole interaction. You have this flow chart here. This is also in your textbook. It really just talks about how you would take a look at a particular substance and going through this flow chart decide whether the operative intermolecular forces are going to be dispersion forces or dipole-dipole forces or hydrogen bonding, and then stronger than that would be an ion dipole force, and then finally the strongest interparticle force, and I like your book for treating ionic bonding this way, would be ionic bonding. So we can call these intermolecular forces, or we can call them interparticle forces, but they range on an atom per atom basis. They're going to range in strength from dispersion, relatively weak, up to ionic bonding, which would be the strongest. All right, time for a couple quick problems. So I have just pulled a couple problems out of a test bank. So here comes the first one. Which one of the following exhibits dipole-dipole interactions between molecules? If you'd like, you can shut off the video and try and reason this out and then turn it back on. Well, if I look at this, I'm just going to work my way up from the bottom. C10H22 is a hydrocarbon decane. It consists entirely of carbon-carbon and carbon-hydrogen bonds. It's an entirely nonpolar molecule. Carbon dioxide contains polar bonds, but the central carbon atom has two domains around it, so it's a linear molecule. The dipoles cancel each other. It is a nonpolar molecule. Bromine is a diatomic molecule between two atoms of the same element, so it has a completely nonpolar bond between them, so it's a nonpolar molecule. Carbon tetrachloride is tetrahedral. It has four polar bonds, but they all cancel each other out, so it is nonpolar. PH3 is trigonal pyramidal. PH3 has a non-bonding electron pair, which gives it a tetrahedral electron geometry, but a trigonal pyramidal molecular geometry. That therefore leads to a permanent dipole in the molecule. So the correct answer is A. Another question, of the following substances, only which has London dispersion forces as its only intermolecular force? So in this case, you are looking for the molecule that is nonpolar, because it's nonpolar molecules that only have dispersion forces as their only intermolecular force. Well, methane has a CO bond and an OH bond and a bent geometry around the oxygen. It's very polar. Ammonia is trigonal pyramidal. We just talked about ammonia hydrogen bonding. It is very polar. Hydrogen sulfide is like water. It's bent. It has a permanent dipole. It is polar. Hydrogen chloride being a diatomic element between two different a diatomic molecule between two different elements. They have different electronegativities, therefore that's a polar molecule. Only methane, which is tetrahedral, in which all of the bonds cancel each other out, is a nonpolar molecule. And so the correct answer here is B. Well, this went a little bit longer than I had hoped. The next QOD video is going to be much shorter than this one. Thanks for watching, and we'll see you in class.